Turn on the audio. Okay, welcome everybody to today's live stream where we are going to be doing live science, and this is on the topic of infrageometry. So we are joined today with Carlos, I am James, and as members of the Wolfram Institute, this is what we do. Live science in public, in the open, so you guys get to join in and see how it's done in real time. So thanks, Carlos. Would you like to just chat about the agenda, the topic for today, and then we can maybe chat a little bit about where we've come so far, maybe what the roadmap is as we wait for the other fellows to join us.
Yeah, thank you very much, James. So indeed, we are just resuming our work on infrageometry. Last time, if you remember, we spent considerable amount of effort just trying to figure out what local functions look like in our framework. We wanted to maybe follow up as much as possible on Nick's suggestion that local edge multiplicities, or basically just multiplicity counts, would give us that structure. And last time we essentially verified that's as good as it gets for the properties that we wanted. So in particular, we realized that the multiplicity counts of edges give us a good additive and multiplicative structure. So in the closest analog of function algebra that we have on our rewriting in our rewriting system of edges on hypergraphs, we do see multiplicities of edges behaving additively under what we call hypergraph addition, which is nothing but disjoint, additive union of the hypergraphs. We also see multiplicities behaving multiplicatively with what we realized was essentially the Hadamard product of the adjacency matrices of corresponding to the hypergraphs. But you can basically extend the notion of Hadamard product of graphs or hypergraphs, which effectively recovers the multiplicative behavior.
Are those kind of the primary local functions? Is there more to add, or with that can we progress?
I believe that we had enough to progress. The whole discussion that we had last time is that we really want to think of infrageometry as being fully framed within our rewriting philosophy, where all there are is hypergraphs and rewriting rules between them. Right? So we have potentially a sort of an infinite landscape of possible hypergraphs, and we have this assortment of rewrite rules that we try to make as simple as possible. We consider the sort of prime rewrite rules in some technical sense that we might want to specify at some point more technically, but for now we're just considering sort of minimal rewrite rules. And then we try to see how those rewrite rules progress our hypergraphs or evolve our hypergraphs, and essentially whether we can observe phenomena that is otherwise known from either differential geometry or algebra, or otherwise sort of the algebraic analog of hypergraphs and things like that. So last time we did realize that all the operations that were being considered, so additive union of hypergraphs that turned into local addition of multiplicity counts, so sort of the additivity property of local functions, the Hadamard product of hypergraphs that essentially amounted to local multiplication of the multiplicity counts, scalar multiplication, which is in some sense a Hadamard multiplication by a constant, so Hadamard multiplication by a uniform hypergraph of uniform multiplicity. All these things essentially recover what is usually known as the ring or commutative algebra of functions of a manifold. And the important piece of progress that we did last time was that we could frame, at least in principle, in a conceptual sense, we could frame all those constructions clearly within a system of rewriting, a system where there's some amount of rewrite rules that essentially allow you to instantiate these operations simply as rewriting events or a sequence of rewriting events. It's interesting, as I made a comment at this point, that the algebras that mathematics typically considers, so for example, the fact that you take two hypergraphs and you throw them together, you consider them together. So that operation is very
like
much
a binary operation, or it could be more than that. Okay.
It's a binary. It could be higher arithmetic. You can add several hypergraphs at the same time, but two for simplicity. That operation, in order to recover it, we if you would like to see it as a hypergraph rewriting process, you need to give some degree of structure to the algorithm so that the final output is the desired hypergraph. So this gets into the subtleties that we've discussed a few times before, where you observe that you have several edges from one hypergraph, several edges from another hypergraph, and you want to construct new edges that effectively come from both hypergraphs in some sense. And so you might want to label those new edges in some particular way. So you might want to consider a joint hypergraph that's essentially just considered simultaneously, and then you do pattern matching on that joint hypergraph. And then the outputs of the pattern matching give you new edges in a third hypergraph. So if you're thinking of colors, you could start with whatever, a green and yellow, and then you get something that's blue or whatever. So in this sense,
what about new vertices?
So exactly. So that's one of the interesting aspects of it. So all of the rewrite rules that we needed to consider to implement local multiplicity behavior or local additivity behavior. So essentially, what we could call generally as infra functions, which is this idea that multiplicities of edge places will correspond effectively. I mean, intuitively, it's kind of, as I said in the last session, going all the way back to the first naive idea that we ever had about infrageometry, which if we wanted to think about a function in infrageometry, we just thought, okay, let's put a number everywhere. So it is that where everywhere stands for place. And obviously place now being both vertices and edges, this kind of edges as places philosophy. But the complication is that having such counts on edges, so basically boils down to this simple picture where you just have numbers everywhere. So in a way, we might want to dial back a little bit or to think, okay, how is this exactly capturing infra functions, right? So
Can you give a quick definition of infra function? Maybe just
yes, sorry, that's actually what we're trying to do. So they did this entire system that you've put together of looking at local multiplicities of your hypergraph.
By the way, Nick is here as well. He's just on.
Yes, hello, Nick.
Hi guys.
So that could be called infra functions. It's as objects. So what I was trying to say is that as objects, they effectively correspond to what was said a few months ago in one of our first live streams, when we thought, okay, let's just throw some numbers, certainly at the vertices, perhaps between the vertices in some way. This was an idea that I proposed even before the edges as places. So I just mentioned maybe we need to, because we were trying to answer this question about what is the analog of continuity or some idea of functions not being completely arbitrary, just being random assignments of numbers. So the fact that they are now correspond to multiplicity counts on the hypergraph, they have values at every edge place, right? That's basically what that means.
So is the function the multiplicity count? Is it like the function of counting? Or I'm trying to just think of it like from a computer science perspective, like a function has arguments and then it gives you something else, right?
Yeah. Remember that the function name is a little bit of a confusing term because it should be understood as a scalar field. So it's something that intakes a point and outputs a number. So that's, if you want the functional perspective, that's the input-output perspective. It inputs a point or place, to be more precise in our terminology. It inputs a place and it gives a number. And the number is the multiplicity that happens at that place, right? In the hypergraph.
And we're calling that an infra function.
So exactly. So I think for simplicity, we could, it's a little bit strange to call that an infra function in the sense that right now, a multiplicity count, or a multiplicity as a general object, you could imagine as something that is mapping a skeletal hypergraph to the natural numbers, or even a complete hypergraph on a given set of vertices to the natural numbers. So you imagine it has zeros basically everywhere where there isn't an edge, and then you have some non-zero values where there are edges, and the value is equal to the number of edges on that location, right, on that place. So, I mean, I'm quite happy to call that an infra function. It's just that it might be a little bit confusing to, because that object really is just a multiplicity count, right? It's just the assignment of multiplicities from the total hypergraph to the skeleton hypergraph, right? Or the skeletal hypergraph. That's, I mean, up to debate, and we might want to reserve the definition of infra function to something that we positively know is going to act like a function. Right now, we have just verified that multiplicity counts behave well for what we want. So they are a very good starting point, and I think they are likely to be very close to what we want. But we might want to say that an infra function is because here's the problem, right? The skeletal hypergraph. So in a sense, what I'm trying to say to gather my thoughts is that in this new setting, everything that we know about geometry, we won't be able to recover exactly. So it's not that the problem here is not that we are trying to come up with a way to just rediscover functions or scalar fields or vector fields or curves exactly literally in our context, because otherwise we wouldn't be doing it. That's not the goal. The goal is to do something that we can mathematically understand as being equivalent or being analogous to some degree to what differential geometry does, and hopefully at some point apply to outputs of the physics project and all the other ideas that we are dealing with at the institute, right? But as a framework, it is more. It could be understood more abstractly, simply as take hypergraphs as grounds for geometry and see how far you can get. And I really like this idea for multiplicities, edge multiplicities as kind of a stand-in for functions, because that means that we don't have to go outside the world of hypergraphs at all. We can use undirected hypergraphs,
as they are. Yeah.
As they are, period. No more structure needed.
And with the rewriting elements as well, that kind of makes it quite neat. I was thinking of, and what I showed you was this idea of using rewriting to get you to the skeletal graph, and like that rewriting rule could be used kind of like as a count. And then like doing like a rewriting rule to as your infra function.
No, that to me seems seems very. I mean, all these formalizations will have to be put into tight definitions at some point, and it's great that we all understand that multiplicities can be computed as some form of rewrite system. Right? They can be computed as some property of a certain rewrite system. I mean, how to formalize this might be interesting, but you can. It seems quite intuitive to me that's last time that we discussed that if you have a rewrite rule that essentially is sending two edges that are parallel, by the way, this terminology, parallel, because to establish to coin some key terms here, parallel means that they are happening between the same number of vertices and they have the same symmetry type. So they have the same orientation.
And the same vertices? Or is that not important?
Same vertices.
Okay.
Same vertices, yes. So basically they are multi-edges of the same kind, right? That's what parallel means. So, if you have two vertices, you can have two undirected edges on the same vertices. Those will be called parallel. If you have two directed edges and they both point in the same direction, so 1 to 2 and 1 to 2, those are parallel. But obviously, if you have two vertices and you have one pointing 1 to 2, but the other pointing 2 to 1, then those are not parallel.
They're not parallel, but they're the same type. They're still the same type. Or is type
they are different. They're different types. Okay. So
okay.
So that's what parallel means. Being, for all intents and purposes of what hypergraph data is, how hypergraph data is encoded, they are indistinguishable.
So type here would be quite a strict word to use for.
Yeah. By type, I simply mean. Normally, we use type as symmetry type or just symmetry. We type. It's not super important to use it in this particular context. It's just a way to refer to the fact that they are existing on the same data allocation, so to speak, on the same memory spots, so to speak, right? So that's what we mean by parallel. So a rewrite rule that sends a pair of parallel edges of arbitrariety to a single edge on the same number of vertices. So it's reductive in a strict sense, right? It's taking parallel vertices. Naturally will give you when applied to any hypergraph, if you have a hypergraph that has maximum arity k, let's say, so your biggest edge has k vertices in it, right? Then you consider the rewrite system given by all the rewrite rules all the way down from k RE two parallel edges into a single k RE edge all the way down to unary, right? If you apply those rewrite rules to a hypergraph, you get a confluent system, and the final terminal state of that system is the skeletal hypergraph, right? Because that's what the rule does, right? The rule pattern matches for duplicity and just reduces the duplicity.
Okay.
Right.
So that's kind of what I was missing with my idea a little bit. Is like, what is the rewriting rule that takes you? Like, what is the pattern match that takes you to the skeletal hypergraph? Yeah.
So the idea was essentially correct. It's just a matter of how we are phrasing what we define, and then the multiplicity counts themselves. We might need to. You might need to specify a bit further or to define a little bit further, which clearly at a sort of local level where you have a single place, meaning a single edge type or an edge configuration. You can consider the sub hypergraph, which is just consider a number of vertices and all the edges of a certain arity among those vertices, right? So if your hypergraph happens to have a bunch of parallel edges among those vertices, if you apply this reductive rewrite rule, right, the rewrite rule applied to that hypergraph is how do you call this? It's actually a sequence. It's not a. It's a one branch tree. It's only a sequence, right? Because there's a single application in the first, because up to isomorphism, right? All the applications of the rule are entirely equivalent, so it doesn't matter which ones you choose. So you apply it once, you apply it again, you apply it again, you apply it again, you apply it all the way from having n parallel edges to having one single edge. at the end, right? And then each step you're doing -1 count of your total edges on that location. So,
but that's like a terminating state for that specific rewriting rule. Yeah.
Yes. So you get to a state in the end. There is a single edge, which is the edge of the skeletal hypergraph, and the number of steps that took you to get there is essentially the multiplicity at that point. Might be the multiplicity -1 or +1, depending on your convention, but yeah, it's essentially the multiplicity of that edge. So I mean, how to make that work in practice, we might want to think about a bit in the future. I don't think it's terribly important to make that infinitely precise right now. Like what it means to how one computes multiplicities with rewrite rules in this very formal sense. I mean, that'll be an interesting thing to codify in the future. But right now, I think it's easy enough to say, okay, we can take multiplicity as information that we can gather from a hypergraph, and we can measure it directly, and that's part of the hypergraph data in some sense. Now, the question is, now that we have this, so the functions interpreted as multiplicity counts need to interact with other objects in the framework in such a way that we get some familiar patterns back. And so I had this notebook from last time. So just to recap where we were, and let me share my screen so everyone can see that.
1 second.
You guys see this?
Yeah. Okay. Can we put that at like 150 zoom? Bottom right, I think. Of the notebook itself, yeah. You can just make it nice and big. Or 125 if that's too big, but yeah, looks good.
Yeah, that's a bit too big for me. Yeah.
Cool.
So what we said last time is that at the end of the process, we have landed in this position where we have a graph, the tangent graph, we call the tangent graph here, this graph, right? Or this one maybe, where you could imagine that these are all undirected. Let's see. What happens if this is testing our hypergraph properties on the fly? But yep, that worked. So you can imagine that we have this graph over here. In fact, I'm going to take this out of here. I'm going to place it down here just for the explanation. Right. So this is the kind of situation that we are going to have with our edge place and the multiplicity functions as multiplicity kind of approach, where you just have an ordinary pairwise graph. There is a distinction between edge places and vertex places, but otherwise they are all going to have multiplicity counts, right? Some of them will be 0, some of them will be 2, 3, whatever, right? The edge count will be the multiplicity of those kinds of edges. The vertex counts will be the unary edge counts on those, right? So we have a nice, finally, in some sense, we find peace between the unary or non-unary or vertex or non-vertex consideration. So vertices, as always, are these sort of placeholders, these sort of locations in memory that are very interchangeable. They're just kind of like standings in some sense. And then the information on top is data that we have on the hypergraph. So if you have unary edges, that means that you have some pure numerical data on those locations. And if you have several higher arity edges, then it means you have some relational information among a few of them. And for now, all we're saying is that you can accumulate several instances of these pieces of relational information, these edges, right? So at the end of the day, what we have is exactly this, right? We have a graph, a pairwise graph that can be navigated and that is populated by numbers. So my suggestion last time was there's two things here, okay? One particular distribution. So this is we could call this the tangent graph of the skeletal hypergraph of a spatial hypergraph, right? So the spatial hypergraph will have as many. This is something that maybe we should debate a little before we barging into it. But to me, just to get some stable terms that we're discussing, right? So to me, and maybe Nick wants to say something else, but or thinks otherwise. But to me, the spatial hypergraph should be the skeletal hypergraph, and having different multiplicity counts on that skeletal hypergraph essentially amounts to having the possible space of functions on a given space intuitively. And if you were to add some edges or vertices, for that matter, to your spatial hypergraph, the skeletal one, then you're technically sort of changing your space. You're doing some operation to your space. You're somehow altering your space. How do you think about it, Nick?
Is that like to be able to say something different to a tangent graph of a skeletal graph of a spatial graph of a hypergraph? Nick, are you with us? I can't hear anything.
Sorry.
Oh, there we are. Okay.
Yeah. So we were thinking what kind of structure the hypergraph represents. What is the space and how to think about what we're trying to describe here.
No, it's just the question that if we believe in this edges as places, there is some discussion. Okay, so let me draw some very simple hypergraphs to make the point. So if you have a hypergraph that looks like this, right? So location 1, location 2, I can live on 1, live on 2, travel from 1 to 2, and so there's one edge. Then if I add another edge, the question is this information spatial or is this information somehow non-spatial? Meaning, does the previous hypergraph versus this one, so this one versus this one, right? Where I delete one of the edges. Like these two hypergraphs, do they have the same spatial information or not? That's basically the question. And I see two possible answers to this. I want to know your intuition or your thoughts on this. The two possible answers that I can imagine are, well, these two hypergraphs have the same underlying skeletal hypergraph that you project down, and it's basically just this one, the bottom one, and therefore they have the same spatial information. The other answer that would make sense to me is, well, these are two different hypergraphs, right? They have two edges. This has two edges, this has one edge. And so this is telling me that between 1 and 2, there is only one edge place that I can traverse to reach 1 from 2. And this one is telling me that there are 2 edge places that I can traverse. So it's basically, in the spaceship traveling kind of picture, it's like there's only one trip through space between 1 and 2. In here, there are 2 trips through space between 1 and 2.
I see.
So How do you think about it?
You're trying to think like of it like a dynamical thing, so that when you're moving, not when you just locate it at some place or not. It's like because I look at the edges and you say that edges are places. I just see that there are two places versus one place, right?
Yeah.
And it's like a location. So we basically, if we're gonna use this analogy, basically there is something that can be located at the same place, but this place is kind of equated to the same, like twice, right? There's two versions of the same place.
Yeah, I mean, but I think the information. Okay, so here's the thing, right? So I am leaning towards the interpretation that multi-edges represent sort of repeated information about the existence of a space between two positions, right? Like in this case, I mean, in a higher order hypergraph, maybe it's maybe clearer to see. So if I draw something like this, and then another one, and I have this. I mean, these are two parallel ternary edges. This is base station 1, base station 2, base station 3, some kind of like outposts 1, 2, and 3. And what I'm saying is that, I mean, it's sort of counterintuitive to say that there exists space between them, yes or no. That's the skeletal hypergraph. The answer to that question gives you the skeletal hypergraph, because the answer is yes, there is space between them. But the multiplicity of edges among the same vertices will be potentially, I don't know, I guess it would make sense that it's communicating or it's encapsulating the different kinds of regions that can exist. Like, in the pairwise case, it's quite obvious, because you can always imagine pairwise relations as traveling information, right? So this is like saying, 1 and 2 are connected. Yes, that's the information of the skeletal hypergraph. The 1 and 2 are connected. No questions there.
I just kind of still confused about the traveling part. So how we can even talk about traveling on the hypergraph when it's just a static picture itself? It's like there's no traveling, there's no dynamics without rewriting the hypergraph.
No, but the point is, okay. I see what you mean. So here's but that's a very good question, because I think that's going to clarify what we are thinking about in terms of infrageometry. So I said it right before you joined the thing, but basically, the goal of infrageometry is to take hypergraphs as structures or as primitive information where we try to do geometric constructions. Where basically we try to, it's like you're Euclid and you're trying to develop your theory of geometry, or you are a mathematician in the 17th century trying to come up with good ways to do calculus or whatever. And instead of the intuition of a piece of paper that is continuous, or the intuition of continuous space that you have, you only exist in a world where hypergraphs are the substance, right? So you can only live on hypergraphs. You can only construct on hypergraphs. So the idea of you moving on a hypergraph is all this messiness that we talked about paths and in hypergraphs, where you can think of moving around the hypergraph in a literal sense. So in the same way that you would consider a function as something like multiplicity counts as a way to purely define it in terms of a static hypergraph, a path needs some form of sequential information. So it will be a sequence of vertices that you visit with the adjacency information of where you go in between them, right? So in that sense, it would be the definition of a path that we gave a few meetings back, where you say you go from vertex place to an edge place to a vertex place to an edge place to a vertex place, and so on, right? And those are the curves of our sort of discrete manifolds or hypergraph manifolds. That's in the sense in which
I just think we need to define what is actually moving, because it's just if you just describe these directions on the hypergraph,
nothing is moving in some sense. Like in some sense, you don't need to imagine that anything is moving, but what you do need, as I said at the end of our discussion about curves, is you define a curve or a path as an embedding of a hypergraph. You can, I'm sure that you can, well, it's not I'm sure, I mean, it's kind of obvious that you can devise a rewrite rule that would essentially compute these paths. And we all know that the rewrite rule should be the sort of composition of paths, kind of rewrite rule applied to the right hypergraph, to the right pairwise graph. But I guess the question here is, my confusion and my doubt here is whether multiplicity of edges, because to me it's very clear that skeletal hypergraphs can encode special information, right? Because a simple undirected hypergraph is essentially a discrete map, right? Because I mean that's what the classic origin of graph theory was, right? The joining of the bridges in the city and all that, right? That classic picture of graph theory and the birth of graph theory in topology and so on is basically when you say, well, I just have discrete information about my locations. I don't need to know the specifics of my locations. I just need to know the basic connectivity topology of it. So from that point of view, it is quite clear to me that hypergraphs can satisfy this property, and we just throw the higher arity connections just for good measure, because why not? But the question is if I draw two edges or several edges, does that mean that there is three different kinds of space between 1 and 2 of the kind that can be traversed to get from 1 to 2 or 2 to 1? Right? The directionality here is just a matter of characterizing the space, right? That we can characterize the space in other ways, and but the question is, how does that play with the interpretation of multiplicities on edges or on the skeletal hypergraph? How does that play out to define things like the directional derivative? I mean, remember that all we're trying to do here is to get to some familiar territory of directional derivatives and have something that starts to look like calculus on these manifolds. Because so far we have constructions that seem reasonable, seem intuitive, but we don't have something that resembles calculus yet, right?
So yeah, that's what we have some. We're trying to build just the mathematical foundations and all. It's like, because I'm trying to think immediately of physics. Like when you say something has to traverse this hypergraph, I imagine, okay, that's what is actually should traverse it, because we imagine everything is made out of space, which is, yes, that's the same structure as the hypergraph. So
yeah.
So it has to be represented as some kind of rewriting. And I would say that like an additional edge as place acts as this additional medium so that it can be rewritten. So if you imagine that there's something as a background, if you imagine that there's some you distinguish between the background and whatever particle is moving, those edges as places can act as this substance that you can rewrite in order to push forward your particle across this background, right? So in that way, it does seems like an additional place.
Okay, yeah. No, I think it's very important that because I mean, sooner or later we'll have to contend with this discrepancy in a way. I think the Wolfram physics approach, where we are thinking of rewriting as dynamics, right? I think that approach is kind of orthogonal to what we're doing here in a sense. And it's a very different philosophy somehow. Like it is thinking that your hypergraphs. So let me formulate the thoughts well, and let me not babble for like 3 minutes before saying something coherent. So in this perspective, you want to think of your hypergraphs as close as possible to what you think of as a manifold in differential geometry. I know I've said this 100 times right now, but what I mean by that is you want to think of the object itself, the hypergraph itself, statically, which you could imagine a single state in a complicated rewrite system that is simulating physics or doing something else. But statically, as a single hypergraph, you want to think of it as an instance of a differentiable manifold. So a differentiable manifold, most mathematicians think of them statically, right? You have a sphere, torus, or whatever, and you just think of it as kind of a static object. But in order to characterize what the static object is, so for example, to say that they have a commutative algebra of functions associated to it and a Lie algebra of vector fields associated to it and all that stuff, you invent all these dynamical objects on top of it, dynamical or otherwise. You invent all these characters that populate the stage that you've set as your manifold, right? And so this sort of...
When you say characters, you mean like analytic tools, like taking a vector field at a tangent on the manifold, different things like that?
Yeah. I mean, you could call them analytical tools, but the way they feel, to me at least in differential geometry, is that these are sort of inhabitants of the world. That the moment that you have a manifold somehow is fully defined mathematically, because you suddenly choose all the equidistant points of a given point in space, in 3D space, Euclidean distance assumed, or you are God-given some set with a Haudor's topology with an atlas to Rn, whatever. Like whichever way you conclude mathematically that you have a concrete manifold, then there's all this population, in some sense, this is kind of ecosystem of beings, vector fields, functions, covector fields, tensor fields, differentiable forms, all these things, they come for free on your manifold. Like the moment you have your manifold, these things sort of pop up, and it's kind of like you have this population. You don't have an infinite, it's an infinite amount of things in a technical sense, in a cardinality sense, but you don't have an infinite set of kinds of things on your manifold. You have only a few things defined. You have your vector fields, you have your tensor fields, they are each of them, and they are infinite, and there are infinitely many kinds of them, and so on. But you don't have things like an assignment of irrational numbers to every point of your manifold, or a 2x2 matrix of Boolean values assigned to every point of your matrix for free. That's not for free. That doesn't come for free with a manifold, right? What comes for free for a manifold is at each point you will have a vector space of equal dimension everywhere. You would get an entire set of things you call vector fields, and they carry this Lie algebra bracket that behaves exactly in this Leibniz root. All these things come for free. They show up for free once you define a manifold. So the expectation here, my modus operandi all this time has been, let's take the hypergraph as our primitive object, the God-given manifold, and then let's see what we can naturally extract from it. And with the constructive tools in the mathematical side, the constructive tools are, we will use the topology, we will use the charts, we will use all the information that goes into the definition of a manifold, which is a very, very thick definition. We have a lot of things there. Instead, here, what we say that we can use is just rewriting on hypergraphs, right? And that's why James's comment on the defining multiplicity counts as some analysis of a particular rewrite, and how we discussed whether we could understand addition of multiplicities, or the additive property of multiplicities as the addition of hypergraphs, and the Hadamard product of hypergraphs as modeling local multiplication of multiplicity. All these things, they are relevant because they point towards the idea that we seem to be recovering something that is conceptually analogous to the algebraic description of a manifold, or vector fields on a manifold, or curves on a manifold, simply with the tools of hypergraph rewriting. So when I say something like, there might be a curve traveling here, we might want to do a path, because my goal ultimately is this: directional derivative is currently the holy grail. If we get a good understanding of what the analog of the discrete directional derivative, or whatever, directional infra derivative, whatever we want to call it, maybe infra derivatives for short, just to sort of coin a term. If we understand that, then we're done. But as you know, taking a derivative in calculus, you require some kind of virtual curve, some kind of virtual movement, even though you're not necessarily assuming that your object is dynamic somehow. Is that a bit clearer?
Yeah, sure.
Okay.
But can you, like, assuming that you figure out what the directional derivative is, can you already, like, build up all the further abstractions on top of that? If you say that it's a holy grail, can you just pretend that you have this function? Maybe we don't know the exact definition of it. Maybe some prototype, just like corresponding to some intuition. Can we already start just actually showing some derivatives of that and definitions that depend on this directional derivative?
I like your comment, and I would love to say, yeah, let's just assume what we know what the directional derivative is, and then we take it from there. But I don't think we are in that position, and I think it's a good position to be in. I don't think we should be in that in the following sense. So I call the directional derivative the Holy Grail, and again, I call it's really quotation marks directional derivative here, because obviously we're not going to have actual directional derivatives in some sense because we're in this discrete space. But differential geometry is built on the notion of directional derivative. It's in differential geometry, it is the cornerstone of manifold theory, of a smooth manifold theory, right? The moment you have that, you essentially just can build everything afterwards. But it's not so much a matter of given more information. It's not that the directional derivatives, you need to provide extra data to define them or anything. But in terms of constructive mathematics, where you begin with a definition of a manifold and then you try to build up to construct things like what is the tangent of a differentiable map, what is this notion of pushing vector fields and tensor fields back and forth, and all this general theory of manifolds where the physics uses. Really, the cornerstone in all that story is the notion of directional derivative, because the notion of directional derivative is, you are now in a topological context where you don't know how to do calculus. You know how to do calculus with numerical variables, because imagine that you've studied high school calculus. You know how to deal with functions that go from R to R. You know how to compute derivatives, antiderivatives, integrals, all these kinds of things on those. But you don't, obviously, I give you a space like a torus or something, or an embedded surface in 3D, you don't know how to do calculus there, right? So the way that you bring your calculus knowledge into this geometric realm is by defining directional derivative. Because a directional derivative, what it does, essentially, it takes the two dual objects of your theory, which is a function and a curve, right? Dual in the sense that a curve is a parameter value into your manifold, and a function is pointing your manifold into a parameter value, right? So you take these two objects, you couple them together with composition, basically. So you say, I'm going to look at the values of this function as I follow along this curve, right? And then that object, curve composed with function, that object then becomes a regular calculus function, parameter to parameter. You can forget the fact that you go into a manifold and you can just do calculus on that thing. You can just compute its derivative. You can compute integrals with it. You're back in the familiar territory. So that's how manifold theory is usually built. You build the theory of calculus for real numbers, and then you define your manifolds with this chart system. And then once you have that, you can pool your calculus of real variables to define things like directional derivative. And once you have directional derivative, which basically combines functions and curves, then everything else follows. And you can define all the other operations that you want, your exterior differential, your Lie brackets, your push facts, push forwards, all pullbacks, push forwards, everything you care about in differential geometry. So to answer your question, my hope with directional derivative is more like, if we get to a point where we have a strong sense that we've understood the interaction between what we think are curve-like objects in infrageometry and what we think are function-like objects in infrageometry, in a way that is analogous to how we understand directional derivatives, that understanding, I think, will be the foundation for what we call in infrageometry. That thing will be what we sort of the first clear step that infrageometry deserves to exist, and it deserves or it grants us a particularly useful or powerful or clear picture of hypergraph analysis that then can be exported and, for example, be applied to states of a rewrite system in a physics model, in a sort of universe generation model, or it can be applied to a complex network that is given by hypergraph, and then you can start to combine some of the techniques from persistent homology or some sort of topological data analysis with the infrageometric approach to just compute geometry directly on the hypergraph itself, right? So that's why I'm saying directional derivative is the holy grail. It's not like I'm thinking, okay, let's quickly define it and then we construct everything else, although that should happen in the medium term. But it's more like if we discuss the problem of what directional derivative is, which is this idea that somehow you travel through space and somehow you see change of something and you're thinking about rates of change as you move through space. That's essentially what directional derivative is about. So if we manage to encode that kind of problem of rate of change as you move through space with the rewrite rule approach and with the hypergraph rewriting that we have done for other operations, I think we will be on the right track, and I think that will be the sort of the first natural direction to go in, right? And the first real advancement of the project. Does that explain a little bit what I was trying to say, or?
Well, that's explained. It just doesn't necessarily provide any concrete direction to follow. Right.
No, no. I was not trying to pretend that I was providing a direction. I was just giving the framing. The important debate to have now, the important discussion is how do we think this can be done? My default guess was I wanted to, if we had something like curve objects, which I think we should think in terms of vector fields, because that's essentially what the abstraction of a curve object in a manifold, if you think about it, is a vector field, because what a vector field gives you is at every point a little curve, right? So that's essentially a good stand-in for a curve instead of, So when I say vector field, you could think it's just, if you look at a point, it's just a curve, right? So, but it's more like having the distributed sense of curve. Similarly with functions, function is just you just want a local set of features of your space that are, scattered features somehow. A directional derivative is this notion that you can couple these two things, right? Given a vector field, given a function, you can pair them together and you get a function out, right? So, which is the function of how does this first feature, this feature function change according to this little curves of the vector field, right? So in traditional manifold theory, this is an algebraic construction, and this corresponds to what people call the dual pairing of vectors and covectors, right? It corresponds to something that is very fundamental in linear algebra, and it's at the core of the construction of tensors and all the higher, more elaborate definitions in multilinear algebra and tensor algebra and so on. So the question was, let's try to see if we can spot that sort of structure here, right? Which we might need to go back to simply thinking, how far are we from the notion that tangent spaces at every point are vector spaces, right? How far are we from thinking of our tangent vectors or tangent edges from the usual situation where they are elements of a vector space that have some addition properties, they have some sort of parallel transport properties that that is only defined infinitesimally and things like that. So that's what I was trying to say, that we need to think of a possible direction in which this may be probed. And I mean, any guess is as good as any at this point. Like we don't.
I've got some crazy ideas, but I'd like to hear Nick's maybe intuition first.
Yeah, let's hear yours. Your crazy idea.
just to get some creative juices flowing. So thinking of the analogy with the physics project, just in the hypergraph rewriting scheme there of the Rudyard with this multi-way process, there isn't this concept of like a physical space, but there's relations to other spaces. Like if we just arbitrarily define a space however you want as like a collection of whatever information or pattern of information in the hypergraph, it's how these patterns relate to each other that could be considered spatial necessarily. And then maybe how they evolve through time, moving further away from each other in pattern space could be spatial, and that could define that change as you have rewriting steps over time could be considered maybe direction. So is this pattern moving further relationship iterations away? Like in other words, like instead of a vertex, you have like a pattern that gets rewritten, and that pattern is like changed to be further away from maybe a similar pattern or some other space in the hypergraph in terms of relationships to where it was before. That's kind of like my idea. Like you have this, you bring back the multi-way component of it somewhat.
Yeah. So that would be my ideal thing to have, to be honest. Essentially a multi-way system encoding or rewriting system encoding of phenomena, which is similar to what, for example, what we were saying earlier for multiplicity functions, right? So maybe an infra function in our setting really is a property of the time lapse that you need to perform certain reductive rewrite rules on your hypergraph, right? Like maybe you can do this in parallel for each place location, and you can do some algorithm that basically just looks at that as sub-hypergraphs, and you just count the number of steps that you have to go on until you terminate. And that's those counts, those discrete counts become the multiplicities. You know, that in some generic sense, that is a property of a rewrite system, right? I mean, I believe that you can, I mean, that information is encoded in the rewrite system as a whole, right? That's why I said earlier, just consider the full hypergraph, the list of rewrite rules given by maximum arity edge all the way, or if you want the entire tower of infinite tower of rewrite rules, who cares? But that's just it's just a specification of rewrite rules, and you put them together with initial state rewrite rules. That becomes a rewrite system, right? We might have more or less direct access to it as mathematicians or computer scientists to study it, but it is what it is, right? And in this particular case, we know that it's going to be always terminating and in fact confluent to a final single state, which is the skeletal hypergraph of the given total hypergraph. So you begin like that, then you spread out in all the possible states in between where you're reducing, and you end up in a single state, which is a simple hypergraph, it's the skeletal hypergraph, right? So in that case, it's a very good point, because this characterizes what I think will be the shape of the answer to our question of what is an infra derivative or something. The shape, it will be something like this. In this case, the multiplicity counts, in my opinion, are encoded, or they are somehow contained in something that can be inferred from that graph, right? That entire multi-way system of rewrites from total hypergraph to the final skeletal one, it's terminating confluent system, so it has very strong properties, and therefore you can do some special, you can extract some special information about it. So similarly, I would expect that the notion of infraderivative is encoded in some kind of rewrite system like that, right? And last time I did mention that we might want to look at like how are these things called? Mass flow in graphs. Do these things have a standard name? Flow network, is that what it's called? Maybe? Yeah. Or flow network or transportation network. Yeah, just check that that's the standard name. So yeah, flow network. It's a very simple name. So I suggested that we might want to look at flow networks and think of rewrite rules that affect the rewrite rules that affect the flow. So effectively, they instantiate the flow in a rewriting manner, right? Because that's what you want to show, right? That your edges interact that way. So the very naive situation is this, right? Like what we said, that say, okay, look, at every location there might be some count, which we might abstract as simply as unary edges, or we might be in an extreme situation. Wait, no, it can't be that extreme because anyway, the point is that you have something like this, and then you just look at this is the flow pattern, right? Where you have a unary edge on the tail of this arrow, and then you have a unary edge on the head of this arrow. You apply this flow rule, and you get this from last time, right?
Yeah.
So you end up on some kind of pattern. So this is the shape of the kind of answer that I'm thinking, but I was going a step before this and asking Nick for his intuition on this idea of multi edges and multi places or whatever, because a function, if we are thinking of our infra functions as essentially given by multiplicity counts, as we discussed, and we're thinking that's a good idea to encode, then it's not so obvious to me whether the flow picture makes sense. And I mean, the flow picture is not so important. I mean, we're not married to the flow picture, but the flow pictures seem to be very somehow
elegant, or it fits in with the
yeah,
style.
just small, neat and small, right? Like, because this might be this here, this directed edges here, that might be a vector field, right? That's the idea. You have a vector field that is like that.
Right? So is it the rewriting rule you choose that gives it those directions on the edges?
Well,
like where do the directions come from?
No, that's the tangent graph, right? So
yeah.
So this is a construction that I mean, if you want to be very very pedantic in some sense, you could just implement this with rewriting as well if you want, where you replace each edge with its edge place vertex and its sort of the directed edges, right? So, where you have this kind of you go from something that looks like this. Oops. Something failed.
You apply, is that applying the rule that I wrote?
No, it's just copying. It should be copying the other thing, but anyway. What I mean is that you might have something like this. Wait, actually, let me see if this works. Okay, fine. So you might have something like this. And then this turns into something like this. Yeah. Right. So you could imagine that this is what some kind of rewrite rule that does this. Right. So if you apply it to your hypergraph, you would get the tangent graph, that you would get the edge place graph, right? If you really want to see the edge, the tangent graph as coming from some rewriting, but the idea is that at the end of the day, you're going to have something, the paths on your hypergraph are going to be given by something like that looks like this. So what I mean is going to be some kind of subgraph of this graph, right? And so you might just want to look at these kinds of graphs and say, if I give you a vector field, which it has exactly the property that you can define a flow with it, because it has a single tail at every vertex, right? That's what we are defining as a vector field, right? So flowing with the vector field is always defined, right? Because you just at every vertex you're pushing in a single direction from that vertex, right? There's no ambiguity of like this vertex flows. Like this is not a good picture of a vector field. This was also not a good picture of a vector field, right? Because we had like more than this. So actually, maybe if I deleted some of these, I guess deleted this one, possibly deleted this one. But it doesn't remember. Anyway, it's not on there. No, doesn't like it. Anyway, that was another one. So yeah.
We had one question in the chat, maybe, just while we're thinking about this. Do you know how the multiplicity values of the manifold influence the curve which can be made from a path?
Say that again?
So do you know how the multiplicity values of the manifold influence the curve which can be made from a path?
Yeah, that's if I understand the question correctly, that's exactly what we are trying to solve here, and that's why I was asking Nick, because the interaction between curves and functions, curves were defined as essentially tracing a path along edges, right? Where you were going vertex place to some adjacent edge place to some adjacent or maybe incident vertex place to some adjacent edge place to some incident vertex place and so on. Right? And you were doing this kind of trace in your hypergraph. So that's why we invented this kind of graph or this kind of graph, right? Because it represents all the possible length one paths of that kind, right? That's why we call it tangent graph. And so that's the question, whether that's why I was asking about these two situations, right? Because the tangent graphs of these two things are different, right? In fact, I have a function for this, right? What's it called? It's positive tangent bundle. Positive tangent bundle. So if this works properly, I should be able to visualize these two things. So if I do this below, I can do positive. I can do positive. Right? That's a good picture to show what I meant, right? They have different tangent bundles, right? Because there are two ways in which you can go to, I think actually maybe this is being rendered. Actually, Yeah. What is this? E1 to E1 to E1 to. Yeah, it only created one, interestingly. But anyway, but it's illustrating my point anyway. So there should be two red dots here, basically. But but that's the whole point. I'm not entirely sure why it's not. I think because it assumed that the hypergraph was simple. This.
Well, if you're making an edge, a new vertex name based on the vertices, then it's not going to be unique. You have to always create some unique, like, index if there are multiple edges that you create this edge vertex from.
Right, because this was adding new vertices based on the vertices of the edges, right? Not on the edges themselves.
Mm-hmm.
Yeah, okay. Yeah. Anyway, so but the point is, you would have two edge places here, one edge place here. That's a pretty dramatic difference. And it would affect how you can flow. Like, this is a considerably richer space than this one in some sense, right? Because you can flow from here, there, then avoid where you came from, and going a circle, and you never cross the same edge place in opposite directions, right? So you can go from 1 to 2, crossing the top edge in the direction 1, 2, and you can cross from 2 to 1 through the vertex in direction 2, 1, right? And you can, but that's not possible here. If you want to go from 1 to 2 and back, you have to cross the edge in 2 different directions. Just to signify that if you're thinking of your hypergraph navigation of how you can traverse it as a sort of an infra walker in your space, right? An infra traveler. These are different spaces.
Yeah, there's more information in the top one than the bottom one. So you could consider it like it's maybe a thicker space with which to move through.
Yeah.
Because
the way I see it. Yeah.
Yeah. No, I was just thinking, like, if you take it back to the analogy and the whole thing about the graphs, you're moving between cities, right? But a curve is supposed to be some kind of rate. It's some kind of like rate of change between discrete kind of points of measurement. It's like, what's different from going from New York to San Francisco and compared to New York to London? There's some kind of change between the first movement to the second movement, or the first relationship to the second relationship.
No, the point is more that with the analogy of cities, edges will be the individual direct connections, right? If there is a road that directly connects whatever London to Oxford, 1 to 2, then you draw one edge. If there's another road that also directly connects London to Oxford, and it's not the same as the previous one, then you draw another one, right? And that's kind of the logic that you. Sorry, there's an insect here. It's bothering the live stream. Okay, it's gone. Yeah.
Can I draw something?
Yeah.
Okay, so that's what I'm thinking. So let's say you have a hypergraph like this, and there's just a few lines, and now there's a section that has like more information, or it's like there's a thicker amount of rewrite rules that could apply in this situation, and then you go here again. So what I was thinking is, let's say you have some kind of pattern, even if it's like a unary edge, there's a rewriting rule that will take you here to the next space. There's some rewriting rule that will take you here, and then that same rewriting rule might take you here. Okay, but at this point, there's multiple rewriting rules that could apply. So your rate is different. So it's almost like you're doing this, and then your rate decreases again over here, or it flattens out, whatever it is. So this might be the curve is kind of like how much energy is required as you move through. And then you could consider like this as a space, And then now that your unary edge is down here, in relation to this space, there's movement. That was kind of my idea.
Yeah, there's some right intuition here. This is what I had in mind. I don't know if Nick, you were thinking in some similar direction, because I keep trying to visualize this movement between vertices when there are several edges, right? And
Can we disclose?
like,
oh, sorry,
this might be important to consider as well. Like, whoops. Oh, it doesn't like it anymore. Okay, fine. Let's see if it likes it now. Come on. Nope. So I think, yeah, I don't know why, but I draw a new one, maybe. Okay. So in this kind of situation as well, right? It's not that dissimilar to what we were saying. Like if we are thinking navigationally in this space, we can go from 1 to 2 via the binary edge or via the ternary edge, right? So if I added a new one, or more, that's just more information on how I can go through there.
But can you move from 1 to 2 via the ternary edge? Because isn't the relationship indistinguishable?
You can.
Okay.
And in our current understanding is that you can.
Okay.
So because that's the entire sort of edge place notion, that you can traverse edges, and so that's the thing, right? Like, okay, yeah. Actually, this diagram I liked because it represents several things. So if you're in 3, for example, right? If I didn't have the binary edges, right, then my path into 1 or 2 essentially needs to overlap, right? I have to overlap in my trip to 1 or 2 if I'm coming from 3, if I only have a ternary edge. If I have the binary edges, then my trip from 3 to 1 and from 3 to 2 can be entirely separate. They can just not talk to each other at all, right? That's basically what the higher arity edges are giving us, right? This idea that of dependence of paths, right? Like you're bundling paths together if the information that you have is that your locations are connected only in this higher arity sense. And by the way, this is why most of geometry and differential geometry in particular is built on simplicial structures, because simplicial structures are characterized precisely by the property that if you have a higher arity edge, then all the lower arity faces, so to speak, are also included, right? Because that's typically how we experience space. That's the usual intuition about space, right? That if I have a triangle of cities, meaning there's space between the 3 cities in a surface, right? In an area, a triangular area between them. I can go from A to B and then from A to C. And I can also just forget about B altogether and just go from A to C, right? And so that's why space, it's this idea that space is continuous, right? Like it's whole. So you always have the boundaries of things, and you can forget about the connectivity to other things, right? Like the fact that London is connected to Oxford is independent of the fact that London is connected to Birmingham and to Cambridge and to all these other cities. Right? It's just independent. It happens simultaneously, but it's independent. That is something that our geometry might not be capturing immediately, right? Like our higher geometry, like we can capture it, we just throw those edges, right? If we want to reproduce actual geometry, then we consider hypergraphs that are simplicial, right? Meaning that if you have an arity n edge, all the sub edges that you would draw in that collection of n vertices also exist in the hypergraph, right? So it might be whatever. For computational reasons, it might be efficient to just encode the highest arity edge, and then everything else is assumed to be there if needed to assume to be there, right? Like it's just a different question. But in terms of process, the rewriting rules that could apply to these things are I couldn't think of anything better than the flow pattern, like this thing. That's why it came to mind, like this kind of thing.
Can we describe why you're trying to get to flow again?
Because that's basically what a directional derivative is in traditional geometry. A traditional directional derivative is just measuring the flow of the quantity of the function that you're differentiating, right?
So if the quantity here are multiplicity counts, then would it be, what is the rewriting rule that outputs different multiplicity counts as it moves around, something like that?
Yeah, it's very strange. I don't have a good understanding of that. That's why I'm confused. That's why I was asking.
Like, what's the raw information of a directional derivative? Like, what is the informational content apart from the analogy or like the image of this line with kind of a flow? These are kind of a very imagistic words.
No. The information is the directional derivative is you provide a vector field, you provide a function. And the directional derivative construction is basically an operation that gives you a new function with two very important properties. It is additive. So if you put two functions in or two vector fields in that are added, the result is added. So it just behaves additively. And if you put in two functions in multiplication, it behaves like a derivation. It behaves like the Leibniz rule.
Oh, that's quite technical. Wow, that's okay.
Yeah. So it's it's technical, but it's a very simple thing. Like, I can annotate on the screen. Everyone will see it, right?
Yeah.
Right now. So you would have something like D that is mapping vector fields and functions to give functions, right? And as a map means that takes X, and I mean, if you want to really be very explicit, X and F, and this basically is like, compute df dt along X, right? That's kind of what it means. So the property is that if you do the X F plus G, the result is dx F plus dxg, right? Same if I do x plus y, but we don't care so much about that maybe. And then most importantly, if you do dx of f times g, then you get the Leibniz rule. You get dx applied to f first applied to the first factor times the second factor outside of the derivative plus of the first factor outside the derivative times dx of the second factor, right? So this is your usual product rule that you learned in high school. Let's call that Leibniz. So that's technically what a directional derivative is, basically. So these two properties here, which is basically linearity or additivity and Leibniz, that's basically what characterizes these things. It's the most important thing. And the thing is, the way this part, the definition part, where I say df over dt along x, that's the construction that uses all the manifold infrastructure. That's the construction that makes use of both calculus on the real numbers and the fact that you have a manifold with your local chart and all your information, right? So the idea is to find the analogs of all these things, find the analog of this, which should be some kind of rewrite rule, and then see if we can somehow find the analog of these two properties, the fact that it's additive and the fact that it's additivity. I'm not very worried about, because it's very clear that our if we are thinking of multiplicity as a function, that is because everything is additive, so it's going to be additive. It's not, that's going to be by construction, basically. But it will be very interesting to try and understand what it means to be Leibniz in some sense, right? Like that would be very interesting. The statement could be understood as, each of these things, right? These things, you have some vector field, which is some information on your hypergraph somehow. And you have functions. We are thinking of functions, if we are thinking of functions as purely hypergraphs, multi-hypergraphs in this sense, right? And the functions are the multiplicity counts of a hypergraph, but you have a hypergraph. Then these statements here could be read explicitly for hypergraph, right? That could be a very naive first approach, where you say, compute, you take f times g, that's the Hadamard product of two graphs, of two hypergraphs, and then you compute the directional derivative along x, whatever that is, right? Might be some rewrite system, might be something. Hopefully the output of that is a hypergraph or something like a hypergraph. And then you wonder if that hypergraph equals to the Hadamard product of the hypergraph resulting from applying that to the first hypergraph with the second hypergraph, and then doing the additive union of that to the first hypergraph with the second applied with the rewrite. So if you can define the directional derivative of a hypergraph given a vector field in it, of a multi-hypergraph given a vector field in it, we could, with our stand-in notions of local addition and local multiplication, we can directly check if that actually behaves like a derivation. I think this approach is extremely naive, but it kind of makes sense anyway. And it could be a good icebreaker, or sort of like starting point for thinking about this, right?
And a function here would be getting a number out. So would the f and the g here be like a multiplicity count in this example?
The f and the g, the f and the g here will be the multiplicity count. So which is all the possible counts, right? Like not one number, but like a number per possible edge, right? Because it's a function is not one number, it's the assignment of a number at each point, right? So in our case, it's a, but
why would it be two different functions? Like if you have a function that gives you those multiplicity counts, then what would a different function be? Like how would you differentiate it?
No, that's the thing. Like that's what we discussed last time, right? So last time we said we want to see if local function addition is additive, right? And we said, well, there will be some hypergraph that corresponds to f, some hypergraph that corresponds to g, and then we just put them together in this additive union construction. Similarly, what does f times g mean? Last time we said that we could imagine it being the Hadamard product.
Okay, so it's the result of applying that those multiplicity counts.
So that's why, like, if we have a candidate for if we have a candidate for okay, let me think. Yeah, if we have a vector field defined in a, or whatever our candidate for what a vector field is going to be on a hypergraph, and we come up with a way to output a single hypergraph out of what the directional derivative of that vector field is with respect to that what the directional derivative of that hypergraph is with respect to that vector field. So if the output of that is a hypergraph, we can directly check if that thing is satisfies the Leibniz rule. So we can directly check whether this resembles a derivation, and therefore whether we are getting anywhere close to we're getting anywhere close to a directional derivative in this sense.
What if
But
what if the arity of the edge is the vector?
But that's the problem, right? Like that's the difficulty. I think that I don't have. I mean, that's why I was asking Nick about this problem of like multi edge, because it seems that we might need to think of a vector field. If you have a multi-edge, does the vector field care about the multi-edges? So you technically, if it's part of the spatial information, definitely a vector field here. So the difference, no, how do I? Oh, yeah. So a vector field here, I'm looking at the left-hand side here with the graphs.
Mm.
So this would be an edge place, right? So a vector field will have a head here and maybe a head here, right? And maybe a head here as well, right? But a vector field here, these are two different edge places, right? So a vector field might have an edge here, then another edge here, and then maybe another edge here, and then maybe another edge here or something, right? So in these two situations, I mean, the spatial, whether we think of multi-edges as having a spatial information or not, is absolutely crucial, even for the definition of the vector field part of the directional derivative, not only for the multiplicity part, but it's going to affect what objects we are considering. So
one thought, sorry to interrupt, thing that I had was like, if there's a binary edge, there's kind of like this direction in terms of the relationship between two vertices. If there's a ternary edge, could you consider there like
why is there direction? It's undirected.
No, I'm thinking of it like if you put the vertices in like a set grid, so the vertices all have like defined points, like maybe they say a vector field or something. If you were to say what is the flow of like in which, starting at any one vertex, if you have that as like the point at which you're thinking about things, and you think of the edge as kind of like an energy, like in which direction is the energy pulling you? So it will, if it's a binary edge, it will pull you towards the only other vertex that exists. It's almost like the line is pointing directly at it. If it's a ternary edge, maybe the line is pointing somewhere in the middle, like between them. It's almost like the direction is not at one or the other. It's like pointing directly between the two spaces. And then if the edge grows, it kind of like, it's always going to change depending on the combination of how many vertices are involved. That was one random thought I had last week. Can I draw a picture?
Yeah.
Sorry, Nick, I'm not giving you a chance to give your input here. I'm just commenting in all the silences. Okay, so let's say here's your edges. vertices. Okay, so I'm just putting them, I mean, they don't have to be stable in my idea, it's just to draw. So let's say, okay, there's an edge here. So if you're observing this vertex here, your direction is very clearly like let's say there's an arrow attached to this thing, and the arrow is going to point like this. Okay, but now if you have
you mean that you have a vector field already, or
not necessarily?
But the edges, the binary edges, are also undirected. This is not a feature of. This is not dependent on binarity.
Yeah, no. I'm just saying if you consider this vertex here at the top, if this is your observation point, then from this point it's looking this way. In a ternary edge, if this is your observation point, you're kind of being pulled in this direction, kind of thing. It's not like a direction, but it's like a kind of it's like a magnet. It's kind of like, where's the magnetism pulling you? And then if you have like a complicated one, let's say like this, a little bit more complicated, it's kind of like, okay, and your observation point is here. You're kind of being pulled maybe there. But the point is this can move around. So if can you move these things? So let's say this green point, it doesn't have to be a vector field. Like let's say this green point is like actually over here. Everything can move around. You just change the angle. But this direction is going to be different to this direction. Or similarly, yeah.
I mean, that direction is pointing to the edge place of the edge.
Yes, yeah.
So that's exactly what we've been saying, right? That you would have a vector, a tangent vector, or a vector general on a vertex place will point at an edge place. So if there is no other edge that is incident on that vertex, then that will be the only possible arrow that you could draw.
So if you add like this, if you increase the arity by 1, then what's going to happen is this is going to move over a bit, and then you.
No. I don't think that's a good intuition.
Okay.
I mean, that's just a drawing. I mean, the information. I mean, there's no such thing as I increase the arity and then things move a little. These don't have good correlates with any of the systems that we're considering, right? Because it's just how we're depicting.
Well, there's the information has changed. So what I'm saying informationally is that there's a direction to the information change. That's kind of what I'm saying. It's not real directions.
The directionality, the vector field. So our current definition, remember that we don't define vector fields intuitively. We define vector fields as what we define intuitively are paths, or intuitively meaning, by definition, we axiomatically pose that this is what we want to mean by a path. And vector fields are a derived definition, which is the shortest length paths from all possible places of your hypergraph. So in particular, that's how a vector is defined, right? As the shortest possible path from each place. So a vector field is further an assignment of such vectors with the property that you only have one tail per vertex, one tail per place. So it will be one tail per vertex and one tail per edge place in your entire hypergraph. But here, the question is, it's not so much to do with that. The question is, if you have, if you going back to this question, is how do you deal with these kinds of things? I mean, I don't know, Nick, do you have any ideas of how would you begin to define an operation that specifying something like a vector field, some kind of information of directed edges on the place hypergraph, would give you a well-defined rewrite rule that maybe is looking strongly to be confluent so that you can define the output directional derivative hypergraph out of it? Do you have any ideas?
No, not really.
I just don't know how to do it. It's just that's why, by the way, I mean, circling back to the point of flow, why flows and why that picture, is that in that setting it was obvious what to do, right? like if you are in this kind of setting, in this kind of setting, it was obvious, right? That you consider something like this. So you have this unary edges as the only masses distributed on your system, and then you have the directed edges as the possible paths that those masses can take. And then you basically just flow the system. So I think, oops, I didn't complete this. So this is probably going to take a while, but yeah, the idea here is, what this thing is computing at the moment, this thing I'm running, is going to take this graph and it's going to apply this rule, which, as you can see, basically pushes a unary edge along a directed edge like that. And so what you can expect is that each rule application, for example, is going to find this one here, the annotations, right? So it's going to find, for example, this one here with this arrow, right? And it's going to push it and it's going to put it here, or it's going to find this one here with this arrow and push it here. And so there will be two if that applies that way, but this at the same time later on might be pushed in this direction. And so, in here, we're going to have, so I think, okay, so this one is going to screw it up because there's a cycle here that the things can cycle here. But if this was a single edge, this would be a terminating rewrite system, right? Because things will be pushed and there will be no cycles and things will be just accumulated in the sort of corners of the graph, right? So yeah, we're still, let me abort that. And can I just delete? Oh no, I did this thing. So I have to probably just take this as.
When you're done with that, there's one question in the chat here. I think we might have covered, but I'll just ask it so long. If multiplicity counts influence the vector field, then multiple edges connecting the same two vertices are like more curvature in that area, perhaps.
Oh, curvature. Yeah, we are far from being able to talk about curvature, but it's a good intuition. That's something that we probably want to think about in the future. But so I think this now should be better. There are no cycles, right? This is acyclic. Yeah. So this should be terminating. So let me just run it for only 3 steps, 3 generations, see what happens. I need to define this as protograph, I guess. And define this and run this and see what happens. See if we can see something at least. Oof. Oh, what? Let me only run it for generations. Make any idea why this is complaining?
Well, I don't see what the issue, just the pink.
Yeah, let me just, oops, it's here. Inherit is not a graphics primitive. Huh?
Hmm.
Let me lower the zoom a little just for this.
I'll just make the vertex size smaller. Why it's so big?
Yeah, something's going on.
Every graph with a unary edge is causing a problem. No, that's not right. What are those black? All the black circles are causing a problem.
I don't know.
Probably.
But at least, I mean, you can see the point. I think.
What has been inherited? Something's been inherited.
Yeah,
Okay, I don't remember.
Anyway, just to make the point here, you can see that things begin as, I mean, this is the actual initial state, just large, right?
Mm-hmm.
And all the system is doing is just flowing. So for example, in this first application, you can see that the unary at 2 just went to 3, right? And then in this one here, you can see that the unary at 4 also went to 3. So this, right? Then you can imagine that now from 3, they can basically only flow. If I keep going, they can only flow to 5, right? Because that's the only direction. So they would flow 3 times to flow to 5, and then 3 other times to flow to 1. And eventually, in this direction, oh yeah, this is not confluent because it's not a vector field, because there's a branching point here. Yeah. So anyway, but the point is that if this directed graph were a vector field, meaning that there's only one vertex per head, right? Then, or sorry, one vertex per tail, then the flow is well defined, and then things will naturally accumulate and terminate, right? And you will have a single final state. So if that was a multiplicity reduced hypergraph, so you can reconstruct the hypergraph back again just by, all your multiplicities at different points are either if they are in a vertex place, those are unary multiplicity counts, or if they are in an edge place, they are multiplicities of that edge, right? Then you have effectively defined an operation that takes a hypergraph, given a vector field defined on it, gives another hypergraph. So we could pose that is the directional derivative application to that hypergraph. And then the question is whether they satisfy some, maybe literally the Leibniz rule. This is what now I'm kind of enticed to get some candidate constructions, because I mean, the Leibniz rule can be checked directly on hypergraphs, right? Because we can do Hadamard product of the first 2 factors, Hadamard product of the second 2 factors, and then addition of that. That's a well-defined operation in the land of hypergraphs, right? With the binary operations of hypergraphs that we've been describing. So all we need is so I guess that one bit of progress that we can claim we've done in the last couple of hours is that we, in principle, could have a direct confirmation or a direct verification that a construction is something like a directional derivative with primitive hypergraph operations, with the additive union, with the Hadamard product of hypergraphs, right? But then we need to make sense of this concept of the directional derivative of a multi-hypergraph, right? That we are thinking whose multiplicity counts are thought of as the functions, right, on that space. And I honestly, that I'm a bit lost. Like I'm a bit.
So
sort of,
maybe to help answer the question just now about curvature, if you could, I thought those things were quite. I thought we were working closer to the idea of curvature than perhaps you mentioned we really were. You said curvature is still like down the line.
I mean, curvature, the problem with curvature is that you really want to measure. I mean, you have to think about what is curvature, right? Like curvature is typically the observation of deviations of curves, things like how curves diverge from parallel transport of each other, these kinds of things, right? So if we are just at the point where rate of change at all, something changing with respect to something else at all, is ill understood, curvature is a bit too much, because curvature, it's interesting, and that's not even going to the more traditional mindset of differential geometry, where curvature is just not defined until you have a metric structure, which is something that we probably want to explicitly think about. But this even connects back to the question of how much of a tangent space structure do we have in our setting, right? How much of the infinitesimal notion of tangent vector do we actually have in hypergraphs, in infra spaces, right? In some sense. It feels like if we were happy with the definition of vector field as this infinitesimal assignment of shortest possible paths to every place of your hypergraph, it feels like we should probably be able to define something like a rewrite rule.
It kind of makes sense, because if you're thinking about moving around your hypergraph, if there was a direct relationship between two vertices, it's kind of like closer in some sense, like. Whereas if you had to be rewritten 3 times to get there, it's further away for any given rule. So it's always with respect to a specific rule. Like, you have to define for this rule how far is something from, or how far 2 vertices away from each other. Because there could be a rule that is like 1 rewrite, they're like, you get there. But then for another rule, you require 3 rewrites minimum. That's the shortest number of rewrites required to get your unary edge or your hypergraph that you're comparing or whatever from one vertex to another vertex place or edge place or whatever.
Yeah, it's unclear to me. Because what I had in mind is kind of a fiction that doesn't fit with the current definition of hypergraphs or spatial hypergraphs that we have. The fiction was, imagine that you only have unary edges, right? But if you only have unary edges, then obviously there are no connecting edges, so there's no edge places. Other than vertex places and edge places are the same thing. So we could try to possibly just try to verify the statement, even at the level of let me pick your brain in case you have an intuition about this. Imagine, okay, so this is an unrelated question. In my head, it's basically what I wanted to start saying last week with this picture, the simplified picture. So if you have a flow network, right, and you define a vector field on that flow network as considering a single edge with a single, per vertex you have a single edge, right? So it's like a vector field. If you define mass counts, right? So each vertex has some, which would be the multiplicity of unary edges if you want to think about it that way, right? and then you flow with this rewrite rule, which basically means that you flow to the final consequences, right? You push all the mass around the flow the sub network that the vector field defines on the flow network. The question is as follows: if you have two distributions of masses, these are like functions, like local functions in a discrete set, right? So they can be added together and they can be multiplied together, just like in the usual way, like pointwise, right? Hadamard style in this sense. The question is, do you think they will satisfy the additivity and Leibniz rule? I think additivity is clear that they will satisfy. Do you think they will satisfy Leibniz rule?
What would exactly? You just defined the. So you have multiple mass distributions and multiple vectors, and you can move them around. What should satisfy the additivity?
Yeah. So what I mean is the following. Like, let me just quickly draw it. So imagine I have some graph like this, right? Actually, let me just use the one that is on the screen already. So I have this one, right? So I'll have some mass distribution that, for example, the one is here is like 1, 1, 1, 0, 0, 1, right? And then I draw a vector field on this, which will be the assignment of this one. Whoops. Would be the assignment of this thing, for example, the assignment of this thing, the assignment of, for example, this thing, and the assignment of this thing, and the assignment of this thing, right? Nope, that's not it.
From the bottom one.
Yeah. Well, this one doesn't have it. Like, this is an arrow pointing here if you want, whatever. So if I choose this, right, and I start with an arbitrary mass distribution, call it like M1, right? It's just distributing weights there. And then I flow with all the possible, like I apply the rewrite rule in a way, like until there's no more rule applications. So the whole thing flows until the thing is depleted, right? So one flows here, everything flows to the final consequences. The question is, if I begin with distribution 1, distribution 2, right? This flows to M1 prime, this flows to M2 prime, right? Two final distributions. It is clear to me that if I take M1 plus M2, the final is going to be M prime 1 plus M prime 2, right? Because mass is conserved, right?
Sure, yeah.
So if I take, yeah. So that's the point. So if I take M2, after flow, I will get M1 prime plus M plus M2 prime. Right. Now the question is, will you get if I take M1 times M2, will you take, after flow, will the final result be M1 times M2 prime plus M1 prime times M2? That's the question.
That's a good question.
Right?
That's what we're looking for, right?
And you multiply element-wise the distribution.
And multiplication is element-wise. Yeah. So it's like Hadamard. It's point-wise multiplication. Yeah.
Wow.
Question is clear, right?
Yeah.
I wonder if there's a quick argument to prove. I mean, this seems like the kind of thing that you could easily prove without having to find it experimentally running some code.
We can think of the final distribution as because that's like a modifying. If you have a finite state machine, right? So you can assign your edges to basically have a transition rate. If there's an edge between two vertices, you chose that particular edge. That's the possible transition that can happen. Right? You can even assign some weights, but you assume that it's like happens with 100% probability. So basically just so your initial distribution is some kind of vector. So you can think of it as just applying some matrix until you reach its fixed point.
Sure. Yeah, but that's basically packaging the rewriting into a matrix, like we've done several times, right?
Yeah.
Yeah.
Can we try a minimal
so
version?
like a special property of the matrix that it like reaches the actual fixed point, so that there is no loops and all that. So you actually have a well-behaved transition rate probability.
Yeah. I mean, that's guaranteed by the fact that this is a vector field, right?
Well, you still can have loops, right? So
no, you don't, right? I mean, you could.
Well, you could have like a triangle there in the middle.
Oh, you could definitely have a loop. Yes. Yeah. I'm assuming you don't, for example, right?
Yeah, but yeah. So there should be some well-behaved transition matrix. So that the actual how do you call it? Stationary equilibrium basically can be reached. Also an equilibrium system, not non-equilibrium.
But but actually, there might be a
dynamical equilibrium.
Wait. But by the definition of vector field, if you do have a loop, right? It's always going to do like this, or an arbitrary number of vertices, right?
Yeah.
So the point is that the counts here, X, Y, Z, are going to be shuffled around, but they will cycle back. So you would under the transition, you would attain some stable orbit, right? Some finite stable orbit.
And so do we like average out over this orbit?
No, I wouldn't average. No. There's no need to average anything, right? It's more like each of any one of them
equal.
Any one of them is a final
Equivalent.
state in some sense, right? Because
so that kind of makes sense to average them out them as a distribution of masses.
Sure. Yeah. I mean, we might want to average them out, but I mean, the thing is, the statement is exact. So the statement doesn't look at averaging. Yeah,
so
sure.
Then your question is like whether it acts as there's a chain rule to what of those states in the orbit it applies to. All of them, or there exists one that it applies to, or what?
No, but the product rule here, this Leibniz rule, applies to the entire distribution. This is a statement for distributions. That's the whole point. So they would be different distributions, but the point is that the three are considered, and hopefully the three are valid entries as an argument equation, and the three satisfy the equation as long as the values for the rest of the graph when outside of the cycle are final positions of the cycle, right? Because in a way, if you have a cycle, the mass flow, by definition of vector field, is unaffected by. No, that's not true, because there could be things coming into the cycle, I think. Yeah, there could be things coming into the cycle. Yeah, but at the end of the process, everything will be in a cycle. Length one cycle being a single vertex, right? So you flow your whole thing until everything is everything is in cycles, and maybe, I mean, I don't know, I don't have a good intuition that averaging will give you the mathematical behavior that you want, but effectively you are sort of equivalencing all those distributions as time flows. It might be that it's very dependent on how you got to that position, so the exact distributions.
Does it matter with regards to what you're trying to achieve here, the m's, the algebra?
Sorry?
Does it matter with regards to what you're trying to achieve with these m's, the masses, and the algebra of the masses? So in other words,
does it matter? What's the question?
Does it matter whether you average or just take an equivalence?
I mean, I don't know. I don't have a good intuition. I'm not saying it's wrong. I'm just saying that averaging over edges seems like a non-local operation somehow. Like all the other operations are local in the sense that they are defined just by adding point-wise, vertex-wise, or multiplying vertex-wise. And averaging is like a non-local operation that you're just mixing several vertices at the same time. Like, again, I'm not saying that's wrong, but you might want to collapse. Like, another way to see this is that you might want to collapse your your cycle into a single vertex and define it as a sink. And instead of averaging, you just add everything together and you say, well, in this sink vertex, which is really the entire cycle, there is a total mass of this, right? And then the picture really becomes that of an acyclic graph, right? Oh, I just saw the comment by memes. Is there an Eulerian cycle function to apply to it? What is the Eulerian cycle function? Not sure. I'm familiar with that. In case memes still. Euler, yeah. Eulerian cycle function is this. Or Eulerian, right? I think that's the.
I'm trying to think of a minimal example. So this is two. This is in so multiplying M1 and M2, then running the rewriting rules should get you M1 times M2 prime. Multiply. And M1 prime and M2 multiply. And you plus those two together. So M1 prime, M2 multiplied will give you okay. So let's take the first case here. So let's say this is blue. So M1, M2, M1 times M2 be 1 would just be that. And take this example. this multiplication will give you this plus this, and then adding those two together will give you okay, those do not look equivalent. I don't know, is this minimal model correct? I might be off here.
I'm trying to draw something similar.
They do not seem... Zero. I think I got this wrong. This is... Might be using the wrong technology to be doing these diagrams.
Yeah, I think my statement seems trivially false with a simple example. Yeah, I think it just seems trivially false.
Yeah.
Yep, it is false. No.
Doesn't it depend on what we do, or what we're doing with this arrow here? We're following a series of rewriting rules, right? So is there?
Well, in this example, we're just flowing everything.
So is there not a flow?
We're just flowing it to the final stable state. But no, but I just
Okay.
just by considering the simplest case of a graph that looks like this. So this simple counterexample just proves that the question is answered. The answer is no. So if you have this very simple case and you put some mass count X over here, some mass count Y over here, some mass count Z over here, and then you consider two distributions. So you could also consider some X prime, Y prime, and some Z prime. When you flow you flow both into the last consequences, what you get in the end is a distribution of 0, 0, then X plus Y plus Z. And similarly here, 0, 0 into X prime plus Y prime plus Z prime. And the question is, if you multiply them together, you get basically a distribution that is on the screen, just times everything everywhere. You flow that together, the thing that you get is, X prime plus Y prime plus Z prime, with zeros above it. So it's clear that this thing is not equal to this thing times this thing plus this thing times the other thing. It's just obvious that the arithmetic doesn't work out.
Yeah.
So it's not. So but that's fine. I mean, it's just an intuition though. It's a curious question.
Because the memes are saying this Eulerian cycle or Eulerian path cycles the graph one edge at a time, i.e. octahedron. Visits each edge until it visits each edge once, allowing for revisiting vertices. Once. Oh, okay, interesting.
Oh, yeah. I see. Yeah, I'm not sure how.
Yeah, it feels like we need to work with the information that the hypergraph and the rewriting of hypergraphs gives us somehow. Like that's kind of like the basis. Then saying like what is the richest sources of these information, and what would be at like a very primitive level, what would be a vector field, what would be the function. And then just try all different types of information. So multiplicity was one bit of information which was interesting. I still have this feeling that something about the arity of edges might be some additional information. But there's different things that we can put into the position of what's going to give us information for to represent the vector field. So maybe it's just a case of iterating over every possible thing that the hypergraph naturally gives us and then seeing if the maths works out. It's like experimentation.
Yeah, this is, and the problem with this is that the entire question is very ill-defined. Like, we don't know exactly what we need. We don't know exactly what we have.
Well, we kind of have functions, so I mean, we can. That's like one step, right? And by have, I mean like it feels solid, like it feels like a solid step. Would the question not be what would be a vector field? Like, what information does the hypergraph rewriting give us, which would work to be a vector field? Is that not a good enough question?
I mean, that's a question. It's just that, I mean, my intuitive understanding was that the vector fields were much more clearly defined and functions were more difficult. And the idea that to take multiplicity counts as some kind of standings for functions essentially is to tell us there's no such thing as functions. There's just that hypergraph. Right? It's just like if you're interested in this particular aspect of your hypergraph, then you're going to obtain something like a function out of it in terms of information. But there's really only a hypergraph, which I like. I mean, this is something I like. Yeah, I'm just seeing memes posting about the Eulerian cycle. Yeah, I don't think it makes that much a difference in this, because the only reason we were looking at this is some kind of cartoon of the more general setting. Like the notion of vector field was definitely different than that of a function, in the sense that a vector field was, as we defined it, maybe this is the problem, maybe this is going to resolve all our issues. The notion of vector field was essentially this artificial assignment of edges at places, right? So almost like we had defined functions as assignments of Boolean values or something, or it was not something that was on the hypergraph and we extracted.
Yeah, that's what it felt. It felt a little bit.
No, but the problem is that I mean, the problem is when we abandon this, like my intuition completely breaks apart, because you could think, if you're really insisting on having hypergraph information, again, given a skeletal hypergraph, then you can define naturally, canonically, by these simple rewrite rules, the additive one in this case, you can define all the possible multi-hypergraphs that project down to your rewrite rule. To your skeletal hypergraph. Skeletal hypergraph, right? That's just fact of life. So similarly, given a skeletal hypergraph, by applying some other kinds of rewrite rules, like the ones that I showed earlier. So if I share this again, can we stop the Viber for a second?
How do I just stop presenting? I think just share screen again.
No, it doesn't let me.
Let me see if I can try now.
Yeah. No. Oh yeah, up here. This rewrite rule, right? That again takes an undirected hypergraph and replaces it by the places, the edge place, new vertex, and the directed edges that connect the possible paths, right? In a sense, this is just it's a well-defined rewrite rule. It's just the data structure here is important because it goes from undirected to directed. So you throw in the information. So if you really want to stay within this perspective, the skeletal hypergraph contains the information of all the possible vector fields as well. Is that true? Well, it contains the information of definitely of the tangent graph.
Yeah.
Right. So, and then maybe that's the problem. The problem is that vector fields themselves cannot be naturally so a vector field, it feels to me like you couldn't instantiate a vector field by doing something like, yes, I'm saying that sprinkling, we use the term sprinkling, we're talking about it, yeah, exactly. So, but that's the idea, that we want to do something equivalent to sprinkling just with rewriting. So I guess it's not obvious to me how you constrain a rewrite rule to give vectors that only have a tail per vertex. Like there's no more than, like you end up with a hypergraph that only has, so you end up with a graph that only has tails, single tails in each vertex. So it's a vector field situation. I imagine you could do that in principle.
I mean, there's a rewriting rule that will, from step 1 to step 2, would move something in a direction that would give it like a tail, perhaps. What if the rewrite step is the tail? Because that's directional. In a multi-way system, kind of the only thing that's directional is a rewriting application of a rewriting step. What if it's a multi-way graph that we actually zoom out and look at and say everything directional is just a rewriting step?
No, that's the other perspective. That's the dynamical perspective that Nick was taking, but rewriting itself is the dynamics. Here we want to see the dynamics statically on the vectors, on the hypergraph. That's the point of vector field. So my question, let me pose a question. If you zoom out and look at the multi-way graph, is the multi-way graph itself not a static hypergraph that we can then put a vector field on? It is, but it doesn't contain any of the space. I mean, it contains the information of the spatial hypergraph only as much as the rewrite rule that generates the graph sees the log information. So that's what it meant in the very beginning by saying that we are doing something that is kind of orthogonal or transversal to the approach of the physics project, where you're thinking of hypergraphs as the static things that are evolved with rewrite rules. Here, we're thinking of rewrite rules as the computational machinery, sort of the spirit of the machine, so to speak, that makes the mathematics work. But instead of formal mathematics made of set theoretic axioms that live in mathematicians' brains. Right?
Yeah, I mean, does it have to be that way, though? That's my question.
Not necessarily, but it's kind of what maybe in 2 weeks we have like a conclusive live stream where we say infrageometry is dead. You know, I'm very happy to bury infrageometry if it has to be buried. If it's really certified dead, there's no problem. Like we can do that. But the game of infrageometry again is to take the hypergraph structure itself statically as containing the information, and all this idea of vector fields, even though the picture is dynamical, it's like, oh, something is flowing, whatever. It's virtual dynamics.
Okay.
It's not literal dynamics. We're not trying to do literal dynamics with it. It's virtual. So it's like considering all the possible dynamics. So, which is this idea that, it's kind of neat if you think about it, that the set of all possible functions on a space is an infinite set. If your target space, the target scalars are infinite, right? Or if your space itself is infinite. But so it's interesting that when you consider functions as multiplicities of hypergraph from a skeletal hypergraph, by applying the additive rules that just basically duplicate edges in every possible arity, you get a similar situation where you start from a state which is your initial skeletal hypergraph, and you blow up, and you never converge. You just keep growing by making the thing thicker and thicker and thicker, right? Not only thicker, but it's just like unevenly thick in different places, right? It's like and that's basically like in some sense generating kind of computationally generating the space of all possible functions on a manifold, right? So yeah.
Here's another random idea. Then it might be too much going into the orthogonal direction, but what if the vector field is like given a hypergraph and given a set of rewriting rules which themselves are hypergraphs, saying like how many potential rewriting rules apply at a given vertex. And then what will be interesting with that is that the higher the multiplicity, the greater that count will be as well. Because for any given rewriting rule, if it applies at a vertex, increasing the multiplicity means it will apply there that many times as well.
No, that's a good idea in general. Like as a concept, I think that's where the definition of a directional derivative is going to be a rewrite rule process. Sure. So the question here is more about the data of the vector field itself. If we make it more or less equivalent to that of the function, should be some graphic structure on top of the hypergraph, like some extra hypergraphic information on top of the hypergraph. Just on top of what I mean of the hypergraph of the skeletal hypergraph, the same way that functions are multi-edges on top of the skeletal hypergraph. Analogously, I would say with some argument of symmetry or some argument of like balance, you would want your vector fields to be something of a similar sort, where you have your skeletal hypergraph, then you put something on top of it that is hypergraphic in nature, same thing, but is somehow. And to me, that is essentially just creating this tangent graph and picking out some edges. I mean that is it's hypergraphic in nature. There is nothing. It's not that we are creating some other substance that suddenly we're cheating. There is no hypergraphs. I mean, these things are still hypergraphs, fair and square. There's nothing. There's nothing really. There's nothing really problematic there. Like even if we like forget for a second the edge place philosophy, so that you are considering this sort of new vertices in the middle of edges. Like even if you go back to the previous interpretation, then you might want to think that a vector field is really just a collection of directed binary edges, right? and that's it. It's like, I don't think that's right, because that doesn't account for paths that can traverse hierarchy edges that we should definitely consider. Like it doesn't make sense that, like, otherwise why would you take hypergraphs? Like, it doesn't make sense to consider hypergraphs, and we're not going to use them, right? But yeah, it's like you can, like, maybe we don't even need this distinction of vertices, right? It might be that vertex places and edge places, just because it might be enough to know that if we have directed edges, binary directed edges on our hypergraph, they are going to be tangent edges in this sense, and it might be fine that we have these new vertices. We might not need to distinguish that ones are vertex places and the others are edge places, because by construction, because of these kinds of rules, we know that only vertex places are going to be connected to edge places, right? You will never have the instance of a vertex place being connected directly to an edge place, or an edge place being connected directly to an edge place, right?
It's bipartite, yeah, exactly.
Yeah, it's bipartite, but the point is that it doesn't. So we don't need to know it's bipartite to treat it as a graph to do some operations on it, right? Because the structure is kind of okay already, right? Like, so I mean, the rewriting. I guess the rewriting will have to be, might have to be careful. But anyway, my point is that our previous definition of vector field was fully graphical in some sense. There was nothing, like, we were not cheating. It's not that functions were more graphical than vector fields. They were, they can be equally defined in terms of hypergraph rewriting and hypergraph data structures. It was just that and even we don't even need to think about vector fields. Maybe vector fields too big, but like even a path, if we think of a path, like if functions are multiplicities, how does a path interact with multiplicity? Well, it kind of doesn't interact in some sense. Like, you go on a path, and what happens is that you might have more than, like, the ambiguity of getting from one edge to the other, sorry, from one vertex to the other, is measured by the multiplicity. So,
but likewise, the arity of the edge also gives you ambiguity, depending on the rewrite form.
Yes, no, sure. I mean, just trying to think, like this situation, right? In here, if I am in one, I see two paths outwards from my position. So I can measure cardinality 2 in a sense. And here I can only measure cardinality 1 when all I'm thinking is about planning my journey, right? So if I'm planning my journey from 1 to 2 in this situation, then I have two choices. If I'm planning my journey from 1 to 2 in this situation, I am just going from 1 to 2. There's no choice, right? So that's kind of how paths interact with edge multiplicity. And this applies to any arity, that this situation is the same, right? Like if this is the one that I had two ternary edges, just the same idea. If I want to go from 2 to 3 and I have two ternary edges between 1 to 3, then it's the same thing, Like I have two possible paths. If I have two edges, I have only one path. If I have one edge, even if the edges order already 1,000, that doesn't change. So path or path ambiguity. I mean, you can imagine that something is going to happen when if you rewrite. So if you have this kind of situation, let's see if this doesn't explode. If you actually have an edge here, right? Let me just make this drawing a little bit prettier. Right? So this left-hand side, sorry, this right-hand side here, right? It might be, well, actually something like this. Let me draw what I mean. Okay, so if so a trip from 1 to 2 on the left-hand side, on the left I have the actual spatial hypergraph, so to speak, right? So a trip from 1 to 2 will be represented in the edge place graph as something like this, like a directed edge to 1, 4, and then 4, 2. So that's the edge place, right? Mm-hmm. So if I had many such edges on the left, right? Because I had multiple, right? Mm-hmm. Then I will have that many different number of paths on the tangent graph, right? On the actual edge place. So if we're doing something like path counting between places, right? Path counting will definitely interact with multiplicity.
Yeah.
So path counting is interesting because path counting takes a hypergraph where your paths are going to lead, and it takes a specification of between what destinations your path is going to be. Huh. That's interesting because this idea of path counting suddenly is kind of clicking into place. In the sense that, forget for a second about edge places, not that forget that there's anything wrong with it, but just like take it just as a tool to think about how paths work exactly on hypergraphs. But imagine that I give you a sequence of vertices, right? Which is kind of my specification of what a curve, like the purest, simplest specification of what a curve should be in a hypergraph, right? Just a sequence, like the same thing as the sequence of points in a manifold. This is a sequence of vertices, vertex places in a manifold. Mm-hmm. Interestingly, the question of path counting, right? Meaning how many paths can you, and maybe some minimality condition, like how many paths of minimum length or something, maybe with some question. Can you find that that essentially trace out that sequence of vertices, right? That question more or less clear?
What is what's the path? It's the sequence of...
Yeah, let me draw on this hypergraph, right? For a second, just briefly. So imagine that this is a skeletal hypergraph, right?
Yeah.
So that's my space. I'm going to specify 2 bits of information, which are equivalent to the curve and the function, and the curve along which I'm going to take the directional derivative.
Okay.
So the function is just a distribution of weights, basically, right? Like I would say, like 2 here, 3, 4, 0, you know, this kind of thing, maybe 1, whatever. Okay. Now, a path will be, so let me use a different color. A path would be a sequence of points, right? So let's say that I start here, which I call this 1, and I continue here, which I call this 2, I continue here, so I call this 3, I continue here, I call this 4, for example, right? So that 1 to 4 and this distribution of numbers, that's the equivalent data to a function and a curve on my space. So there is a natural, oh no, but this is just a number. What am I saying? This is just a number. It's just a number.
What do you mean by just a number?
No, sorry. I was going to say something like the number of paths that you can define on this hypergraph, on the thick hypergraph, that traverses this whole thing, right? Like you can go from 1 to 2 in 3 different ways, because there are 3 edges of this kind, right? So I can go one way, because there are 3, right?
Okay. Yeah.
I can go from 2 to 3. I can go again in 3 different ways, because there's 3, right?
Sure. Yeah.
There's the 3 edges here. From 3 to 4, I can go in 4 different ways, right?
Yeah, but there could be a binary edge between 3 and 4, as well as that ternary edge, right? So then you could go in 5 different ways.
There could be, but there isn't, right? So,
but my point is, there's not just one type of edge between.
There could be. So you count it. That's my point. Like you totally, like, I don't know, could have chosen this part of the hypergraph. You just count it, right? Like it depends only on the edges that exist there, right? It depends only on the incident structure. But I don't know what you do with that. Like that's I don't know what you do with that.
What do you mean? That would be a flow?
No, but that's the problem. There's a problem.
I like this idea of ambiguity. I mean, that could be like the more ways you can get from one place to the next, the greater the flow or something. If there's only one way, the it's like a higher and a lower amount over different vertices.
Yeah. I don't know.
So I mean, the
I really
question to know whether this would work is you would have to construct that thing with the algebra of would that work out with the mass. Remember we did the algebra with the mass.
Yeah.
Is that how we would check? In other words, how do we check that this is a good intuition?
No, I think it's a bad intuition. That's the problem.
Okay.
I mean, this is not. I mean, it's an interaction between a function and some kind of information of like some path-like information. But like you have the combinatorics of the paths that you could follow, that join those locations.
Yeah.
Those, I mean, they are going to satisfy some arithmetic, right?
Yeah.
I mean, essentially, what is it? You have basically multiplication of those things, right? Is that right?
What, like a path multiplied by a path? Or...
No. What I mean is that the number of different paths between 1 and 4 equals 3 times 3 times 4 here, right? Yeah. Like it equals the amount of paths between 3 times the amount of paths between.
But why don't you just make it one path, and then you say there's a rate of change as you like along the path. There's weights at different points.
No, we don't. That's the point. We don't want weights. We want something that is purely count based, because it's deep down. It's just a hypergraph. It's just the discrete bits that are being rewritten, or because we know that if it's arithmetical like that, if it's the number of paths, we will be able to pick it up with our rewrite system. That's part of the point.
That's okay. I see.
So we will be able to, that kind of stuff. We would say, how many times can you embed? Like this is basically what I said the other time, right? Like a prototype path that goes from 1 to 4, right? Like that goes 1, 2, 3, 4, right? In those directions. Like the number of times that you can embed that in the actual hypergraphs, that's just the rewrite rule, right? If you have this hypergraph exactly with these extra edges that we just drew here, you can just pattern match and rewrite and find that as some kind of rewrite system question, right? But I don't know. I mean, I have no intuition why this should be a good thing. I'm just finding an interaction between something that looks like a path and the multiplicity of edges, which is what we have been thinking as function.
Well, the idea of a path fits in nicely because you have to travel along a path. You can't, if you're going from one city to the next and then there's another city beyond that, there's no way to get to that other city without going through the middle location first. You have to go along it. With the edge places situation, like what you're saying is like as soon as you get into the edge place, there's no distance. There's no like idea of like actual distance between an edge place and a place. Like a vertex and an edge, there's no distance between them, but there is definitely a distance between two vertices.
Yeah, I don't even know how to think about this. Nick, do you have any insights? Come to the rescue, any chance?
No chance, though.
And do you agree that there's a problem with like making path interact? Like how do you have a strong sense that paths in hypergraphs should be like the edge place construction is good for paths on hypergraphs, or how do you feel about these things?
Well, I feel you just should try anything.
Yeah.
Yeah, we're really trying to experiment, so it feels like what we need to do is have a test for candidates of what would make a good vector space, and then just be able to throw a bunch of different ideas at that vector space test.
I don't know. I mean, if like the thing is, we do have a nice template, because if we take to heart the point of view that a multi-hypergraph encodes a space with functions, or a space with a choice of function, let's say, right? Then rewriting on that hypergraph could be a good stand-in for calculus. It's something to do with that function. So if we invent some way of rewriting on that hypergraph that essentially amounts to compute the rate of change of the function on the space with respect to a given curve, then we do have concrete questions to ask, which is, if you take two functions on the same space but the same curve, do you get some behavior that is multiplicative according to the Leibniz rule, for example, right? Or these kinds of things. Because otherwise, I don't even know what to check, right? Like my only reference point is the Leibniz rule. So I would want to find some kind of indication that we are doing something like the Leibniz rule. I mean, it's very hard to explain. Or like, if we had something like the Lie bracket of vector fields, where the Lie bracket of vector fields is usually derived from, or could be derived from the Leibniz rule being a bit more fundamental in a sense.
Mention what you meant by the Lie bracket again, like if there's a way to do Lie bracket.
Lie bracket is just it's basically the commutator of derivations. So derivations are the ones that behave like the Leibniz rule. So it might make sense to think of the Lie bracket in isolation, just thinking in terms of vector fields graphically, but
I looked at the Leibniz rule a little bit. Not the Leibniz rule. I looked at this Lie bracket idea a little bit previously as a potential for like multiplication, which obviously you explained is not the right way to do it, because we're not going from vector fields. We're trying to find the function, the hypergraph itself. But I like that idea. So it's kind of like, as you move down one path, given another vector field, given one vector field, and then you move down the other path given the other vector field, it's like, what is the difference in the ending location if you do one versus the other first, sort of thing. And then that difference is the, what do you call it, the
Lie bracket
variance, yeah. And then it's that at every point. That's how you when you commute the two vector fields, it's like those differences at every point is that commutation, right? Something like that.
Yeah.
So it's kind of like saying at any point, like if you start at 1 here and you follow a specific path, given a rewriting rule or whatever, versus what if you take a hypergraph as the rewriting rule, where does that end leave you? Or going the other way around, given the hypergraph of the rewriting rule, if you take the initial hypergraph as the rewriting rule, like you swap around what's the hypergraph and what's the rewriting rule, and then say what are the different locations that you end up, and then take that as the Lie bracket variance. Because, okay, so bear with me. So you got like the hypergraph, that's your state, and you have a rewriting rule, and then the left-hand side of that rewriting rule is a hypergraph itself, right?
Yeah.
So what I'm saying is, if you take the hypergraph A and you apply the rewriting rule, what are all the paths that you end up at? Okay, and then so that's like your first set of numbers. Then you swap them around. then you say, okay, if you take hypergraph B as the state and you apply the no.
No, but you don't show up with the rewrite rule itself. You just do something like you have two rewrite rules, and then you apply the rewrite rule. I mean, the concept of a commutator of a transformation is what the libbracket is implementing. So, and again, that's the direction that we should maybe like schedule separate live streams where we say now we're going to take the physics project approach where rules equal dynamics.
Okay.
Here, rules equal algebra. That's kind of the two slogans, right?
That's a differentiation, yeah.
So in Infrageometry, rules equal algebra.
Okay.
In physics project setup, rules equals dynamics, right? And it's a very, very different approach because in a sense, if rules equals dynamics, you are thinking of your space of possible hypergraph as this sort of larger thing that kind of a meta universe where you can exist, and then you are traversing it with dynamics, right?
Yeah.
And like,
so you want to leave that for like later on sort of thing. You want to leave that.
I don't think it's necessarily later. I just think that as of now, I think of them as very different things.
Okay.
I think of like, honestly, to me, the way you do mathematics, I'm trying to model the Infrageometry project as closely as possible to traditional mathematics, but replacing set theoretic notions of where you say this is defined as such, and open sets, and there exists, and blah blah blah, and all your finitary notation to describe all these infinitary objects, all that stuff, very long tradition of set theoretic mathematics that has been super powerful and so on. I'm trying to replace all that exists in pen and paper papers and articles, and human brains. I'm trying to replace that with a finitary hypergraph rewriting based framework.
Got it. Okay, so it's the approach. Yeah. Okay.
Yeah. As such, your hypergraphs should be the primitive information, and everything should be defined in terms of hypergraph rewriting or an algorithms thereof. And you can assume maybe some computer architecture. All these things are fine because that's what mathematicians have done. Mathematicians have stored things in lists, and they have stored things in their memory, and they have drawn diagrams, and they said things are here, and my axioms are immutable, and this is like all those things have been done in sort of soft matter coding, right? In like programming of biological soft matter.
Biological
now the point is we can do this with this sort of computational substrate, but we pay some big prices here. We're paying the cost of finitariness. We're paying the cost of completeness, that every time we do something, we need to do it all the way because it's a finite structure. And, so that's why we are using this approach of rewriting and so on.
We've got a question here. Perpetual Science just joined us. Maybe he can give some insight. Sounds like it's...
Oh, Perpetual Science. Hey, so we are actually unfortunately at the end of what I think is today's session is now 3 hours of going on Infrageometry and basically making no progress. But it's very important.
We ruled out something earlier, like falsifying the theory is good, right?
That's true. No, we did make progress, but not of the satisfying.
Okay, let's summarize it up. While we stuck in where we are.
Yeah. Let's summarize it, and it's going to be as a good summary, as a closer stream, and take it from here next week. We seem to have a strong intuition that functions, the infra functions, are probably related to multiplicity counts of hypergraphs. This comes from the fact that hypergraph algebra, so things like hypergraph additive union, hypergraph, what we're calling Hadamard multiplication, which is basically doing the Hadamard product of the adjacency matrices of the hypergraph, and so on, really faithfully recover the behavior of local functions in a space. So that gave us the confidence to say, well, then we will take a skeletal hypergraph as our fundamental topology, so to speak, then populated hypergraphs with edges, multi-edges and so on, as the standings for the data of a space and a function. Similarly, we have the edge place interpretation that allows us to understand quite well the notion of paths, the notion of proximity in a space where you can be living at a place, and the proximity of your things around you depend on whether you're on a vertex or on an edge. We're thinking of vertices as sort of like the landmark locations, and the edges more like the sort of in-between space that is just there to account for the fact that things can be connected, but not so much that they exist in a independent, unique way. Under this conceptions, we are trying to get something that resembles the construction of a directional derivative, because that is, in the traditional presentation of differential geometry, that's the foundation, that's the cornerstone of the theoretical edifice, the formal edifice of differential geometry and calculus and manifolds and things like that. So we had some intuitions about reducing the information of the hypergraph, the multi-hypergraph, down to something that might look like a flow graph. And we pondered whether the flow graph was could have some behavior under flows, under some assumptions, to mimic the behavior of a directional derivative. We very easily saw that the small examples already prove it wrong. So there's no direct easy link in that sense. So I mean, it was something that we ruled out, but in itself, it was already kind of a cartoon version of what we are actually trying to represent. And now we are stuck because perpetual science saying, I love directional derivatives. Yeah, they are great. And now we're stuck because we would like to have a prescription of how to take a directional derivative, which essentially needs to reduce to some rewriting procedure to act on a given multi-hypergraph, right? And we are thinking that it should be related to, like, the data that you are provided is some path-like data. It could be a vector field, to be the most analog to a vector field under our definition, which is at this point I would even say contentious, given that we are not making them work as vector fields yet. But some path-like information, that's or curve-like information, let's leave it at that, which is going to involve some kind of directional edges between vertices at some point. And a bit of information of that kind, and a bit of information that is basically a hypergraph with multi-edges. So it's a stand-in for a function in our context. And with those two bits of information, hopefully combined, they provide enough contextual information for some kinds of rewrite rules to apply. And those rewrite rules, maybe in a very natural way, produce a confluent final hypergraph that can be interpreted as the directional derivative of that function along that curve-like object. And we might see some properties of some properties of the directional derivative in the abstract. So things like additivity, things like the directional derivative of a constant is zero, things like the directional derivative of the multiplication of two local functions satisfies the Leibniz rule, right? These kinds of behaviors that we want to understand as abstractly as the directional derivative. That's what we want, right? And that's the kind of thing that we need. But we are lacking that. We are lacking what is the rewriting prescription. I mean, we're actually lacking. Last time we thought we were lacking more the function part. Now it feels like we are lacking more the curve part of the specification because, but really, I feel like this is just we are just juggling the uncertainty and the ignorance in some sense. We're shuffling it around. It's not a one, but in any case, we are missing the approach that will condense as a rewrite prescription that ideally is confluent, or at least under some reasonable assumptions is confluent, and will produce a single hypergraph as an output, so we can directly check some multiplicity properties or some Leibniz properties or things like that. So
but ultimately, we're trying to get to a directional derivative, and what we need are functions and a vector field to make. Is that too summarized, or is that?
That's basically the case. That's basically the case. We need. I mean, where it sounds like we are back at square one. It sounds like we are defining functions and we are defining curves, and we want them to like so now we have a lot.
So we got a feeling for functions, but the point is, it only felt good because of some assumptions we made for what could be a vector field. But if that assumption's not there anymore, then our idea of functions might not apply at all. It's the combination of both of these things that could give us a directional derivative that makes them valid. It's by themselves. You could define it however you want. It's the composition of all of this.
Not entirely. Like we, because of the discussion in the previous stream, we did make substantial progress in the direction that the multiplicity counts do appear as nice standings for functions, precisely because of what we figured out. This notion that additive union essentially amounts to matrix addition, that local multiplication, local point-wise multiplication essentially amounts to Hadamard product of the adjacency matrix. These things are, those are two observations that are very trivial, and in hindsight, it's like, how didn't we think of those originally? But they do provide some sensible connection to traditional geometry, right? And while being very elegantly just hypergraphs, just about hypergraphs, there's no need to wait over anything, or like technically you can remain at finitary, rewrite friendly, rewrite ready kind of hypergraphs with minimalistic kind of looking rules. So we have made some conceptual progress. I mean, I'll be meeting Stephen, and I wanted to report on this because this is important progress. But completely unclear how one makes the construction for the directional derivative.
Any message that we could relate to Carlo Rovelli?
Carlo Rovelli. So I don't know. I know Carlo indirectly as well.
Send him the link to the stream.
Yeah, just tell him if he knows how to do discrete directional derivatives. I'm sure that he's thought about it before, knowing his work.
Okay, I need to shut off in about a minute or two.
Yeah, me too. It's been long, but hope. It
feels like we covered a lot of ground. So it was.
We thought a lot.
A lot of thinking happened.
This is just the nature of research for everyone watching. I mean, there are days when you just go in circles and you just heat up, but you don't do much. You don't travel far.
Well, our step count was high, so that's sometimes that's what counts. Yeah.
We can feel good about ourselves intellectually, definitely. Anyway, thanks a lot, James and Nick, for being here. Especially, if not a lot of progress is made, hopefully at some point we get our things done. And Nick, I'll probably send you some questions because I'm gonna prepare the notebook for Stephen, and we'll there'll be some functionality just to illustrate things.
Okay. Sounds good. Okay, until the next one. Tomorrow we're doing a live stream which is going to touch on observer theory and maybe some technical advances that we could look at for observer theory. So be sure to join in there. Dugan's just joined in the chat as well. So that's going to be it'll be interesting for Dugan's opinion on if he rewatches this. We covered a lot of ground, but we kind of at a bit of a an impasse, or not even an impasse. We have to, yeah, it's we traveled a massive circle around the map of possibilities, and we got back to where we got back to base camp, and now we have to decide which route to travel next week.
Yes, exactly. Yeah, we need to recalibrate. But yeah, thanks everyone in chat. Memes for visual science. Dugan, good to see you all. See you soon.
Okay.
Bye.
All the best. Bye for now.